Hello and welcome to our discussion on linear approximations and differentials. Basically what we're going to see is how we can use the equation of the tangent line, which we get from taking derivatives, to approximate a curve. The picture on the right illustrates this idea. The blue line is our curve, our function, right, our f of a, and then the tangent line of course hits at this point a, comma f of a, right? And we can see that the equation of the tangent line, this red line, is awfully close to the actual function on a decent interval around a, right? From about here to there, they look like they're pretty much right on top of each other. And depending on how precise you want to be, you could maybe even go as far out as here and here and still have a very small error in, when you're talking about the difference between the values that you're getting out of the straight line versus the values you're getting out of the function, right? It's all about what would f of x be for the function versus the f of x we would get out of the straight line. Right, so the y, the outputs. So we're going to use these linear approximations to give us a result when it's too cumbersome or too difficult to actually get that result out of the function itself. Okay, so we know that we have this general formula for the equation of a tangent line, and that just comes from our standard y minus y1 equals m times x minus x1, right? That's the standard point slope formula of a line. Here, y1 is the y value, the f of a, right? That's just the y value at a, and then x1 is just a, right? So all they're doing is they're rewriting this standard point slope formula in terms of a particular point a, and then of course the slope is the derivative evaluated at that point a. Then what we've done here is we've solved it for y by just adding that f of a to the other side, and we can see that our function, right, y equals f of x, is just equal to this equation at that point a, and then we can approximate it. We can say that the function, the original function, remember this is the one in blue, is approximately equal to the values we get out of the red line, right, the tangent line, as long as a, the values of x are pretty close to a. So we can't deviate too far from this point a, right, the tangent at that point. If we needed to go a long distance away, we would just have to kind of do the process all over again with that new value a, find the new tangent line that's now a good approximation to the function at that new value. Okay, so equation 2 is just kind of giving this thing a name. You can see that it's the same thing. It's still f of a plus, right, the derivative at a times x minus a. It's still basically the equation of that tangent line, only now we're going to give it a new name and say that's what we're going to call the linearization of f at a. So that's why it's capital L. That's just the linear approximation of the function at that point a. Okay, let's run through an example and you'll see how this works. Let's say we have a simple function, the square root of x plus 3, and we want to figure out what's happening at the point a equals 1. Well, when a equals 1, you plug in 1, you get 1 plus 3, that's 4. The square root of 4 is 2, and that's easy. So we know what the function equals at a. It equals 2. That's simple. But what happens when we want to be close to 1, right? So a little bit on each side of it. A little bit bigger than 1, now all of a sudden you've got 4.05, a little bit smaller than 1, all of a sudden now you have 3.98, and we can't take the square roots of those, at least not by hand. Of course we can do it in a calculator and things like that, but if this was something that we wanted to calculate by hand, we can't do that, but we can do it with derivatives and linear approximations. So we can take the derivative of this function, we now write it as a power rather than a square root because it just makes it easier to figure out the derivative, right? Power comes down, power minus 1, clean it up. Algebraically, that's the simplest way to think about the derivative of the function. And now, if we look at the function evaluated at 1, right, so the original function evaluated at 1, which we already talked about, that's 2, and then the derivative of the function evaluated at 1, you put a 1 in here, and you get the square root of 4 again, right, which is 2, and you get 1 over 2 times 2, there's your 1/4. Okay, well now if you plug all of that into our formula here, f of a is now f of 1, right? F prime of a is f prime of 1, and we're looking at x minus 1. Pulling in all those things, we know f of 1 was 2, we know f prime at 1 was 1/4, and then we have x minus 1. We do some algebra, and this ends up being the equation of the straight line, right? The linear approximation. Now your book and these slides are going to keep talking about it in this form. I like writing it as just one fraction. It's going to make some of the math easier later. But the reason why we write it this way is it just kind of reminds us that it's an mx plus b, right? This is a 1/4 x plus 7/4. There's our slope of 1/4, right? So mx plus b. Okay, so according to this, this is now a squiggly equals, right? A linear approximation to the original function whenever x is close to 1. Remember, we got to remember that this is only valid for a small neighborhood around 1. If we want to do a linear approximation around x equals 2, we would have to redo this process all over again, get a slightly different, right, formula for the tangent line. We get a slightly different slope and a slightly different L of x, right, a slightly different linear approximation, and we could redo this over and over again for any a that we're trying to figure out. Okay, so now when we're trying to figure out the square root of 3.98, it's really just what is x in this case, right? To get 3.98 out of this, x needs to be 0.98. And so that's why our approximation is now going to be 7/4 plus 0.98x. If you were using my version, right, sorry, that should be a 7, of 7 plus x over 4, it's the same darn thing, right? It's 7 plus 0.98 over 4, and there's your 7.98 over 4, and then there's your 1.995. Same thing if you want to do this one, you get 2.0125. And it allows us now to calculate square roots without having a calculator. And you think, well, that's kind of stupid. Who the hell cares? Because we all have calculators. And why would we ever need to do this by hand? We wouldn't. This is just a learning tool. This is just showing us that we can use these linear approximations to calculate these things. And in fact, if you do break out your calculators and do the square root of 3.98, you will see that the answer you get out of your calculator is 1.99499 blah 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 blah, and that rounds pretty darn well to 1.995. And then of course if you want to do the square root of 2.05, you get 4.05, you get 2.01246 blah 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 blah, which also rounds quite nicely to 2.0125. Okay, so these linear approximations are pretty close. They're not perfect, right? They're approximations. That's why they're squiggly equals. Here's the picture that illustrates what's going on. We're basically finding values on the red straight line instead of trying to find values on the curved blue line. And we can see that, as I stated before with the results, that they are pretty good, but they're not going to be good over a long interval, but they will be pretty good over a somewhat limited interval. Here are some examples. If we did this over and over again for these different values of x, we can see from the linear approximation versus what we get out of the calculator, they're all pretty darn close, within 10, 100, 1,000th, more or less, even better on some. When we get down to here, right, as we're getting further and further away from that a value of 1, you can see that it's now starting to deviate quite a bit. There's quite a big difference between 2.5 and 2.449. Right, this would really, if we rounded, maybe 2.45, we're still off by 5/100ths. That could potentially be a big difference. Just depends on, the application and how close we want to be. So as we said, and from the picture, you can see that the accuracy is pretty close as we stay close to that x of 1, but as we get further and further out, the distance between those two lines does get to be a little big, and it just depends on what your definition of how big is too big, right? How much can that error be before we need to shift the point and do it all over again at a new a. Well, the next example is going to show us how we can actually determine that interval, right? If we want to set the limit for our error to be a certain amount, we can figure out how far out our neighborhood can go until the difference between the linear approximation and our function becomes too large. So the question is, how far out can we go and keep the linear approximation within 0.5 or within 0.1? We're basically saying if you take the difference between the actual function and the linear approximation, right? How big or small can x go until that difference becomes bigger than 5, right? We want 0.5, sorry, we want to keep it within a half. So the distance, right, absolute value is a distance formula. That's saying the distance between those two functions. So it's basically saying how far out can we go and have the gaps, right? We're looking for, we need to keep these vertical gaps have to be smaller than a half. And we can see that they're going to get pretty big down here pretty soon. But in this direction, maybe not so much. Okay, well, we can solve it with a calculator by graphing and zooming and doing those types of things, or we can do it algebraically and actually solve it by hand, which is a better way. It gives us a more accurate result. But if you were to graph it by the calculator, all that's happening here, right, if you remember how to solve an absolute value inequality, you take the stuff inside the absolute value as it sits, and again, just because it's going to be easier to write, I'm going to write it this way. And you set it less than 0.5, but then it's also greater than the negative, right? That's what it means to have absolute value less than something. This number is a positive, which is less than this, or a negative, which is greater than the opposite, the negative 0.5. And then what you can do is you can subtract this from both sides, right? Multiply by a -1, all the signs are going to flip, and you're going to end up getting this equation here. I'm going to do it slightly differently. Rather than subtracting and multiplying by -1, I'm just going to add this piece to all three things and go from there, and you'll see that it's the same darn thing. Here, the way they did it, it's a nice illustration, because when you add the 0.5 or subtract the 0.5, which is what you get right on either side, you're basically getting the same function plus or minus that half. Then all that's happening is your function is being shifted up and down by a half, and that's the other two blue lines. And then you can see that the top one actually does intersect the original linear approximation, and that tells us that this is going to be our interval from here to here. All of those x values are going to be within the right distance, right? They're going to be in a good neighborhood where our error isn't going to be bigger than 0.5. And if we zoom in on the calculator, we can find that those two values are roughly -2.6 and +8.6, which looks about right from the picture, right? That looks like about -3 and about +9. But if we want to do it by hand, how could we do it, right? Now, for those of you that don't care to do it by hand, feel free to fast forward through all of this. But I just want to show you that this is something that we can very easily do with some algebra. So we'll start again with the original -0.5 less than the square root of x plus 3 minus this x plus 7 over 4 piece, right? And then less than 0.5. So I'm just going to start with our normal compound inequality that we get when we're trying to solve an absolute value inequality. Now what I'm going to do is I'm going to add this piece to both sides rather than subtracting and then having to multiply by -1 and flipping things around and doing it. Just seems cleaner to just add this piece. So now we have x plus 7 over 4 minus, and I'm going to write this instead of 0.5, I'm going to write it as minus 2/4, right? Isn't that a half? Less than the square root of x plus 3, and then add it. Remember, you got to add it to all three pieces. X plus 7 all over 4 plus 2/4. And you can see why I did it this way, because now I can make it all one big fraction. So this is going to be x plus 7 minus 2 is plus 5 all over 4 is less than x plus 3. And remember, these go over the whole thing. And then 2, right, 7 plus 2, so this is x plus 9 over 4. Now, I'm going to multiply everything by 4 to get rid of this fraction. There are numerous ways you guys could do this. If you wanted to try it by hand first and then come back and look at how I do it, feel free. I do this just because now with a couple simple algebra steps, this seems like a much easier thing in my mind's eye to solve. I know that in order to solve for x, I need to square everything to get rid of this square root. So you square all three pieces. When you square the left-hand side, you get x squared plus 10x plus 25 less than 16 times x plus 3, right? Because remember, when you square it, you got to square both pieces. And then over here, x squared plus 18x plus 81, right? FOIL that out if you don't have the pattern memorized. Now, the middle, x squared plus 10x plus 25 less than 16x plus 48 less than x squared plus 18x plus 81. Okay, now we've got a couple quadratics with a linear thing in the middle. Hopefully you're thinking, well, the only way I can solve this with a quadratic is to have a quadratic related to 0. So why not subtract this piece from all three pieces and then have a quadratic less than 0 and then another quadratic greater than 0, and you're basically solving two quadratic inequalities. So subtract 16x and subtract 48 from both sides. You get x squared minus 6x, right, because it's 10x minus 16, and then 25 minus 48 gives you negative 23. This is less than 0, is less than, and when we do the same thing on the other side, we have x squared, 18 minus 16, right, is plus 2x, and then 81 minus 48 is plus 33. Okay, so now you can see we have two different quadratics, green and blue, both being related to 0. So if we want to do the green one first, we're basically trying to solve x squared minus 6x minus 23 is less than 0. Now you could try to factor this thing, but it's not going to factor nicely. So you're better off going straight to the quadratic formula. So minus b plus and minus the square root of b squared minus 4 times a, right, which is 1, times c, which is negative 23, all over 2a, which is 2. Now we can also do the same thing for the blue one. Right, so just so we can see the colors, this is the green one. We can also do the blue one at the same time and have minus b, so this is negative 2, plus and minus b squared, which is 4, minus 4 times a times c, all over 2. And you can see right off the bat we're going to have 4 minus a big number. This is going to be a negative number in the square root. And so the blue one ends up having no solution. At least no real solutions, right? These would be imaginary numbers. So that's nice because now we can only have to worry about concentrating on this one. 6 plus and minus the square root of 36 plus 4 times 23. Well, let's just do that for us. 4 times 23 plus 36 ends up being 128 all over 2. This is divisible by 4, which is nice because then it pops a 2 out here and we get 6 plus and minus 2, and then what's left over on the inside is 32. And the only reason why I did that is because now I can write it as 3 plus and minus the square root of 32. Those are our two roots, those are our two solutions, and those are going to give us the same two numbers roughly that we saw from the calculator. In fact, if you do the square root of 32 in your calculator, you'll see that this is roughly equivalent to 3 plus and minus 5.657, which is basically 3 plus and minus 5.66, right? Which is going to give you negative 2.66 and 8.66. And I wrote the answer up here from the previous that we got from the calculator, negative 2.6 and negative positive 8.6. So you can see that we get the same thing both ways. Technically a little different because of rounding, but that's because we did it algebraically and they did it by approximation by just looking on the calculator. Okay, so there is a slight difference. Ours is more accurate than theirs. But you can see that it is doable, right? So we now know that if we want to stay within 0.5, if we want that error, the difference between the value that we actually get out of the function and the value we get out of its linear approximation, if we want that difference, that error, that change in height between the two functions, if we want that to be less than 0.5 or less than a half, we have to stay within, right? X, the X values that we plug into our linear approximation have to be between negative 2.66 and 8.66. They rounded, right? That's why theirs is 0.6 and 0.6. They rounded down. They said if we make that interval a little bit smaller, then we know we're safe. We actually know that we can go out to a little bit bigger than 0.6, negative 2.657, right, with our approximation, and 8.657, and still be within a half as far as our error is concerned. And if we want to do the same thing to be within 0.1, it's the same idea. We could do the math all over again. I'm not going to waste our time with that. We're going to get answers of negative 1.1 and positive 3.9. Again, that's just the window where our error is within a certain amount. Okay, so you might be asking yourself, so what? Why the hell would we do any of this? Why can't we just deal with the functions normally? Well, you can. I mean, we can obviously deal with the function, the square root of x plus 3 normally very easily. But sometimes the functions are a little bit too cumbersome, a little bit too difficult to work with. So linear approximations are used in other sciences. They're not usually used a lot in math because we strive for accuracy, but oftentimes in the applications of it, physics, biology, chemistry, economics, they will use linear approximations just to make the calculations easier. One particular instance of that is the formula for the period of a pendulum. We can obtain that expression as negative g times sine of theta, and that's that expression is the tangential acceleration of the pendulum. It's how fast the pendulum is accelerating. Well, to make the calculations easier, oftentimes they'll replace sine of theta with the remark that sine of theta is very close to theta as long as theta is not too large, i.e. as long as theta is close to 0. Because we can use a linear approximation, we can use this technique of linearization of the function sine of x at a equals 0, right, at the origin, and we can show that the line just y equals x is very close to sine of x at 0. But as you go away from 0 in either direction, it starts to deteriorate. So we can use that approximation of swapping out sine of theta for theta, right? Same thing as sine of x for x, as long as we have small thetas, small x's. Another example occurs in optics where they'll swap out sine of theta for theta and cosine of theta for 1. Again, the linear approximations will show that those things are fairly accurate as long as your theta is close to 0. Okay, the ideas behind these linear approximations are sometimes called differentials. If y is equal to our function, right? So if y equals f of x, where f is some differentiable function, then we know the differential dx is an independent variable, i.e. it's the change in x, right? And dx can be given any value we want. We can keep it really small, we can make it bigger, right? But basically the change in x can be whatever, and then whatever that is determines what the change in y is. So dy, the differential, can be defined in terms of dx. And it basically comes from the idea that f prime of x is just another way of saying dy dx. Multiply both sides by dx, and f prime of x times dx equals dy. Ta-da! That's where this comes from. And you can see that dy is now a dependent variable that is defined, right? It depends on the values of x and dx because it is defined by the derivative of the function at x, right? That's f prime of x. That's an x. Right? And then times dx. If we look at this picture, that helps to kind of figure out what's going on. If we start at the point P, right? So we're starting at the yellow point, and there's our x. If we travel this distance, we now have x plus some change in x, some delta x. And then we evaluate the function again, we get this point Q right here. And this change in height, this delta y, this change in y, corresponds with this change in x. But if we're dealing with the linear approximation, right, the slope of the tangent line, if we're dealing with the tangent evaluated at P, we get this line, and then if we try to evaluate this linear function at this same x plus delta x, instead of getting this height, we would get this height up here. We'd be up here at r, and that's this height of dy. And we can see that this change in y, this little blue delta x, is equal to the function evaluated at the new value x plus delta x. So if we go over here to x plus delta x, we evaluate it here, we get this height of the red dot, and then we subtract the original height of P from it, and that's that change in height, right? So this is my delta x. That's just showing you how much the function has changed. Well, dy is how much the linear approximation has changed, and you can see quite clearly from the picture that there is in fact a difference between the two, right? That distance right there is your error. Call it E. That's the difference between the dy and the delta y. Well, we can compare those two values and see just how big that error is. So if we want to compare delta y and dy for the function, and we're going to have to actually define what the function is, x cubed plus x squared minus 2x plus 1. And x is going to start at 2 and go from 2 to 2.05, and then we're going to try it again and go from 2 to 2.01. Okay, so in the first case, we can evaluate f at 2 and get 9. And 9, right, this value here, ends up being this height. Right, that's f of 2. Here's 2, and there's the height at 2. Well, now we can also evaluate what's going to happen at 2.05. This is the point 2.05, right, where delta x equals the 0.05. Now if we evaluate the function at 2.05, we get this height right here, right about there. This looks a little high. Let's lower that. Maybe right about here. And that's the 9.7 0.717625 that we get from here. And so the change in y, this distance here, is just literally the difference between those two. And it's very simply the 0.717625. Okay, that's delta y. That's the change in y on our actual function, which I wrote here to remind ourselves. But let's figure out what dy is, right? Remember, dy is just equal to the function evaluated at x times dx. So here is the derivative of the function. Remember, the original function was x cubed plus x squared minus 2x plus 1. Take the derivative, that's where you get 3x squared plus 2x minus 2 times dx. When x equals 2 and dx equals delta x equals 0.05, we always set our dx to be the change in x that we're actually doing, the delta x. Then if we plug all that in, we evaluate the derivative at 2, we multiply it by the change in x, and we get this dy of 0.7. Well, delta y was 0.717625. And the difference between those two is not that much. That's our error rate, right? That would be the error, that would be the little tiny distance here. I'll highlight it in green. That distance there is the difference between the two, between the 0.717625 and the 0.7 that we get from the differential. Okay? We can try it again with 0.01 and see that we get a delta y of 0.14, blah, 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 a dy of 0.14, and the leftover bit, right, this amount here, is the error, because it's the difference between those two numbers. It's the amount over, right, that we are, or under, depending on how the approximation goes. Okay, our final example illustrates the use of these differentials in estimating how big these errors can actually be. Again, this is going to be kind of a simplistic example. It's used to teach the method. Obviously, in a real life situation, you'd be doing this when you have something that you cannot measure directly, so you have to use the differentials, and you just want to know how bad your error is, or what's going to be kind of the maximum range of that error. So for this particular example, the radius of a sphere was measured and found to be 21 centimeters with a possible error of 0.05 centimeters. So they just know that maybe their instruments could be off by a little bit. And we want to know what's the maximum error in the value of the volume of the sphere if we use this measurement, right? How far off could our volume be if we're using this radius measurement? Well, we know that volume is related to radius by 4/3 pi r cubed. If the error in the radius is denoted by a change in r, right, a dr, then the corresponding error in our volume is going to be our change in v, kind of our delta v. And we can figure out what delta v is by just taking the derivative of this formula, and that's where we get change in v, right? Delta v is equal to 4, because the 3 came down and canceled the 4/3, 4 pi r squared dr. Now, when the radius was 21, which is what we had measured, and we knew that the possible error was 0.05, if we plug all that in, we get 277 as the maximum error that we can get for our volume. And that seems like an awfully big number, and it does. But when you consider how big the actual volume is, it's actually a relatively small error, and that's why we normally do a relative error rather than an absolute error. And the relative error is just take that error and divide it by the thing that you're measuring, and then it gives you kind of the error as a fraction of the thing you're measuring. So we take the measurement for dV, divide it by the actual measurement for V, do some simplification of algebra, and we see that the relative error in measuring the volume is equal to 3 times the dr over r. Well, dr over r is just the relative error in the radius, right? Because this is dr, that's the error in the radius divided by r, the way we measure the radius. So it just tells us that the relative error in our volume is equal to 3 times the relative error in our radius. Our relative error for our radius was the 0.05 divided by the size of the radius, which gives us this very small fraction. And when we multiply that by 3, we get a little bit bigger, but still relatively small fraction. And then if we talk about these in terms of percentages, it's just easier for lay people to understand it, right? This 0.0024 is 0.24%, and this 0.007 is 0.7%. So that means that if we have a relative error of 0.24% in our radius, which is what this represents, that's a 0.24% relative error, then we're going to result in a relative error of our volume that's going to be 0.7% or smaller. And so that's it, guys. That's differentials, how to interpret them, how to use them. Its application is normally reserved for more of the applied sciences, but it's still a good thing to look at in calculus.